the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is another video in a series on orthogonality and least squares for linear algebra students. At this point, we're going to step into the definition and concepts of orthogonal sets. That's all we're going to focus on in this video, but it is actually an important topic as we move forward and talk about orthogonal bases and orthogonal matrices and orthogonal projections. So this is kind of required material. In fact, everything we try to teach you in linear algebra is required within the course, but definitely this stuff is solid building blocks for the rest of the course. So here it is, definition of orthogonal and orthonormal sets. So a set of vectors u1 through up in Rn is said to be an orthogonal set if each pair of distinct vectors from the set is orthogonal. So in other words, maybe we have 10 vectors in this set, something like that. Each of those vectors is orthogonal to each other. So vector 1, u sub 1 here, is orthogonal to u2, u3, u4, u5, all the way to u10, or up in this case. u2 is orthogonal to u1, u3, u4, u5, all the way to up, and so on and so forth down the line. And just to remind you, two vectors are orthogonal if and only if their dot product is 0. So each of the dot products of the vectors within the set is 0. So by definition, that set, if all the dot products of those vectors were 0, would be called an orthogonal set. And I suppose I could have just read on because that's exactly what this says right here, right? That u sub I dotted with u sub j is equal to 0 whenever I is not equal to j. Now, if S is an orthogonal set and each of the vectors in S has a norm of 1, then we would call S an orthonormal set. So not only are all the vectors orthogonal to each other, but they all have magnitude 1. This type of set actually is ideal. It's what we would call, like in R cubed, the unit vectors. It's 1, 0, 0, 0, 1, 0, and 0, 0, 1. Those are orthogonal to each other and they're of unit length. So therefore, they form an orthonormal set. So let's just do a quick example here, nothing too terribly mind-blowing. Let's show that these vectors form an orthogonal set, but not an orthonormal set. Again, to be an orthogonal set, we'd need the dot products between each of these vectors to be 0. And that's exactly what we get. Also, I should mention here, the dot product is commutative, so there's no need for me to take a look at v3 dotted with v1. I already have v1 dotted with v3, which is the same as v3 dotted with v1, and so on and so forth. So there's no point in me commuting these dot products. Now this shows that these vectors form an orthogonal set, but we still need to show that they're not of unit length. Technically, v sub 2 is of unit length, but all I need is one of them to not be of unit length for the entire set to not be orthonormal. And there we go. The magnitude of v sub 1 is the square root of 5, so therefore the norm of v sub 1 is non-unit. It's not equal to 1. So just this group of conditions right here tells us that the set v1, v2, v3 is an orthogonal set. Now actually part B is important for us as we move forward. We really would love our sets to be orthonormal if we could, so we're going to normalize these vectors. Now remember, when you normalize a vector, it doesn't change its direction. Therefore, these three vectors will still be orthogonal to each other when we normalize them. I will call the normalized version of these vectors u, so u sub 1, u sub 2, u sub 3. All right, a couple things I want to mention now that I've gone through and I've normalized these vectors. The very first thing I want to mention is the terrible notation I used right up here. So the decent notation is this. that the normalized vector u sub 1 is the vector v sub 1 divided by its magnitude. That's okay. But then when I wrote the vector v sub 1, I actually wrote it as a column vector divided by the magnitude of v sub 1. That's actually pretty terrible notation. In reality, you'd like to just write this as 1 over the magnitude of v sub 1 times the vector v sub 1. It's just a little bit more commonplace, I guess, in mathematics to write it that way, because it looks really odd with a vector being divided by a scalar otherwise. I mean, it's not incorrect, it just looks weird. The other thing I want to mention is that the second vector, v sub 2, had a norm of 1, so it didn't really change in this entire process. But again, in the end, when you normalize a vector, its direction doesn't change, just its magnitude. So those three resulting vectors, u1, u2, and u3, now form an orthonormal set. Pretty easy to do, right? So let's follow that up with a theorem here, kind of an important theorem, one that will drive a lot of our theory as we move forward. If we have a set of vectors, in this case we have p of these vectors, u1 through up, that's the set that we're calling S. Okay, so if we have a set of vectors, and that set of vectors is an orthogonal set of non-zero vectors in Rn. So each of those vectors has n entries, and all of them are non-zero. And finally, they all are orthogonal to each other. Then S is linearly independent. Visually, that should make sense. These are orthogonal vectors, so I think naturally we tend to understand they should be linearly independent, and hence they form a basis for the subspace spanned by that set of vectors. Again, this is fairly natural for us to understand. If you have these orthogonal vectors, you could think of them as the standard basis for example, r squared or r cubed or r4, and they're orthogonal to each other. Obviously, they create a basis for the space spanned by the set of those orthogonal vectors. However, that type of understanding is not a proof. So let's go ahead and start by saying S is that set of orthogonal vectors. So it's an orthogonal set of non-zero vectors in Rn. And the implication of that is that the dot product of any two vectors within that set will be 0 as long as those are not the same vectors. Now we want to showcase that this set of vectors is linearly independent. So let's go ahead and consider the following equation where the constants that you see right here are scalars. And you probably should remember that equation. That's the linear dependence relation. This is how we're going to either show that a set of vectors is linearly dependent or linearly independent. And if those vectors are linearly independent, then all those constants, c sub i's, should be 0. Should be the only solution to that equation, but we're trying to prove that. Well then, it should be the case that 0, the scalar, should equal the 0 vector dotted with u sub 1. And I'm using u sub 1 here without any loss of generality. In other words, you could have chosen u sub 2 or u sub 3. It doesn't really matter. And at the end of this proof, I'll state that again. But this should be true. I hope everybody would just nod their heads and agree with that. But that is equal to, since we know that the 0 vector is this linear combination of the vectors from S, our orthogonal set, then we can trade that 0 vector out for that linear combination, and then we can use the properties of the dot product to rewrite that as this. And all I did was use distribution there. And by the way, I'm missing a plus right there. But remember, each of our vectors is orthogonal to each other. That is, if I is not equal to j, then u sub I dotted with u sub j should be 0. So everywhere where we have a dot product in this summation, that dot product will turn into 0. That is, this dot product right here will be 0 because u1 is not up. The dot product prior to that will be 0. The dot product right after this u1 dotted with u1 will be the dot product of u2 with u1, and that will be 0 as well. So the only survivor is this guy right here. That's the only dot product that does not turn into 0 because remember, u1 through up, these are non-zero vectors. So a non-zero vector dotted with itself is always greater than 0. But again, because all the other vectors in this set are orthogonal to u sub 1, the dot product between those vectors in u sub 1 will all be 0, so everything else turns off, and we get this guy right here. Now we happen to know 0 is supposed to equal that. Well, remember, u sub 1 is non-zero, so u sub 1 dotted with itself is going to be positive. Well, that's going to imply then that c sub 1 must be 0. And because I did this argument without any loss of generality by stealing just u sub 1, I could have replaced that u sub 1 with a u sub 2 for this entire argument. And all I would do is just replace all these, and we get down to that right there. So no matter what, the only survivor in this linear combination will be c sub I times u sub I dotted with u sub I. However, u sub i's are never 0 in this orthogonal set because we specifically said it had non-zero vectors. So that means c sub I must be 0 for every single I. And that's what I say here. Since u sub I is non-zero for all I, c sub 1 must be 0. A similar argument shows that c sub I is 0 for all I. Hence, the set S, which is u sub 1 through u sub p, is a linearly independent set because the only solution to this equation here is the solution where C1 through CP are all 0. There we go. We've proved it. But don't let the proof pull you off the path of what this theorem is saying. If you have an orthogonal set of non-zero vectors, that set is linearly independent and is therefore a basis for the subspace band by S. We'll finish out this video with a quick example. There's not much to this example, but it's still nice to see. Suppose that we have a subspace called W of Rn, and it's spanned by n non-zero orthogonal vectors. Explain why W must equal Rn. Let's go ahead and let W equal the span of U1 through Un, where the set U1 through Un is an orthogonal set of non-zero vectors, because that's exactly what they told us it should be. Well then, by the previous theorem, that set, which I'll call S, is linearly independent and is a basis for the subspace spanned by S. So we have n linearly independent vectors forming the basis for a subspace. That means the dimension of the span of that set of vectors must be n. Because Rn has dimension n, S is a basis for Rn, and therefore the span of S, which is equal to W, must therefore equal Rn. It's very, very fast, kind of a nice argument, not much else to it. Anyhow, that's all I have for this video. It's just a gentle introduction to orthogonal sets. Again, this idea of orthogonality and then orthogonal sets is going to play a big role as we move forward. I'll see you in the next video, hopefully, which is called Orthogonal Bases. Have a great day. Be a wonderful human being.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.